the tabular method for integration by parts is one that we can use anytime we have a u that will eventually differentiate until we get 0. When this is useful is typically when you have x to some large n times another function and you need to use integration by parts several times. So here's what this looks like. With x squared sine of 4x, we're going to let u be x squared. We're going to let dv be equal to the sine of 4x. We're going to start with u and differentiate it until we get to 0. Then for however many rows we have, we're going to start with dv, which would be the sine of 4x. You don't have to include the dx part of it. It's just v prime, really. We will integrate, so the integral of, with the first one, the integral of sine of 4x dx, you would require a 4 here. So you would need a 1/4. And that gives you 1/4 times negative cosine of 4x. So that's where they get that. You repeat that process until you've filled in all the rows. And then you want to alternate the signs. So we're going to start with positive, we'll start with negative, positive, negative, until you fill all the rows. And then we're going to multiply across and add all of the pieces together. So when I say multiply, I mean like this. I'm going to multiply the positive times the x squared, and that's going to get multiplied by the first derivative, or the first antiderivative. And we're going to follow that trend. So the integral of x squared sine of 4x dx is going to be positive x squared times negative 1/4 cosine of 4x minus 2x times negative 1/16 sine of 4x plus 2 times 1/64 cosine of 4x, and don't forget plus c. So this gives me negative 1/4 x squared cosine of 4x plus 1/8 x sine of 4x plus 1/32 cosine of 4x plus c. And if you follow the last video and do integration by parts multiple times, you would see that you would get the same exact answer. Keep in mind, you can only do this if u differentiates to 0 eventually. So let's look at some examples. I've got the integral of x squared e to the 2x dx. So with this one, I'm going to list out my u and my v prime. My u I'm going to choose to be x squared. My v prime will be e to the 2x. So I'm going to differentiate that until I get 0. So we'll have 2x to the first power, 2, and 0. I need to at least figure out what the pattern is going to be here with the integral of e to the 2x dx. I would need a 1/2, or sorry, I would need a 2. So that means that I would need to multiply by 1/2 on the outside. So this is 1/2 e to the 2x. Now if you observe that the constant out front is not going to make much of a difference, we're basically going to be multiplying by 1/4 each time, or 1/2 each time. We're going to end up with 1/4 e to the 2x and 1/8 e to the 2x. Now remember the tabular method draws a diagonal line here. So we're going to multiply there, and then we're going to alternate the signs. So I end up with 1/2 x squared e to the 2x minus 2 times 1/4 is 1/2 x e to the 2x plus 2 times 1/8 is 1/4 e to the 2x, all plus c. And that will be my answer. Here I'm going to let u be x cubed. And I'm going to have my v prime, which is going to be the e to the negative 2x. So we'll build our table, x cubed, e to the negative 2x. So I'll differentiate 3x squared, that'll give me 6x, which will give me 6, and that'll give me 0. So we're going to have that many rows. Now keep in mind, you want to know what happens with e to the negative 2x dx and kind of have a good idea there. U is negative 2x, so du would be negative 2 dx. So I need a negative 2 here. So what I end up with is basically every time I integrate the integral of e to the negative 2x, I multiply the outside by a negative 1/2. So repeating that pattern, I have negative 1/2 e to the negative 2x. Negative 1/2 times negative 1/2 will give me 1/4. Multiplying again, I'll get negative 1/8. And multiplying again, I'll get 1/16. You know you're done here because you've run out of rows from your u. Don't forget to alternate your signs. So we will have negative 1/2 x cubed e to the negative 2x, go down here, minus 3/4 x squared e to the negative 2x. 6 times negative 1/8 is minus 3/4 x e to the negative 2x. And then 6/16 is going to give us that negative 3/8 e to the negative 2x, all plus c. Now, if we had done this one with integration by parts, we would have had to have repeated integration by parts 3 times. So this does make our life quite a bit simpler just by avoiding having to do that. And for this last one, I've got u, which I'm going to let be x cubed. I've got dv, which I'm going to let, or v prime, which I'm going to let be sine of 3x. So we'll differentiate here, 3x squared, 6x, 6, and 0. And v, or the integral of sine of 3x, you notice that you would need a 3, which means we need a 1/3. And when you integrate this, you get negative cosine of 3x. So negative 1/3 cosine of 3x. Now this one you might want to be a little bit careful with. If you integrate the cosine of 3x, again, you need a 3, so we're going to have to multiply by 3 on the outside. And I get negative 1/9. But the integral of cosine of 3x is actually just cosine of 3x. So I get negative 1/9, I'm sorry, sine of 3x. So I get negative 1/9 sine of 3x. Integrating that again, we're basically back to this version. It's just we start off with a negative 1/9. So we got to multiply it by negative 1/3, which gives me 1/27 cosine of 3x. And then this one we had to multiply by a 3, so that's going to give me 1/81 sine of 3x. If you need to integrate each one individually, please feel free to do so. Otherwise, you may want to just play around with the constants. So I'm going to have, using the tabular method, alternate my signs and do those diagonals. So I get negative 1/3 x cubed cosine of 3x. Plus 3/9 is 1/3 x squared sine of 3x, plus 6/27 gives me 2/9 x cosine of 3x, and then finally minus 6/81 gives me minus 2/27 sine of 3x, all plus c. So that would be my full answer there. That is the tabular method.